Bem, boa tarde. Well, our next speaker is Professor Michael Kosorok. He's a professor in North Carolina, Chapel Hill, North Carolina, and he's got his degree, his PhD in the University of Washington, and he was a former professor in the University of Wisconsin Madison. And, well, it's amazing that he has also a master degree in music composition. So we have somebody here that has a nice, master degree. So he's gonna talk to us in precision medicine, in machine learning. Uh, Welcome.
Well, thank you. I've enjoyed my visit greatly so far. It's really been enjoyable. The food is fantastic, and everything else is good too. I'm going to talk about something, I guess, completely different than other things that's been talked about so far. Um, it's a sort of a new area of direction that um, me and several others have started to go into. Some of you, I think, have started working in similar areas as well. Um, Looking at precision medicine and machine learning and their relationship with each other, and some research directions that are created from them. Um, First, I want to talk a little bit about personalized medicine and specifically the kind of question that I'm trying to answer statistically that our group is focusing on. So let me just say a little bit about this. There are several terms that are used that are somewhat interchangeable: personalized medicine, precision medicine, individualized medicine, stratified medicine. Now, the one thing that I want to just be a little clear about is that there's also this idea that every single individual will get the treatment exactly that they need, specifically for them. We're not quite that far along with the process yet, and so mostly when we talk about precision medicine, we're talking about finding very small subgroups who are treated similarly. So it's statistically difficult to get down to one observation for this. So, but I want to point out that the idea of developing targeted treatments that take into account individual heterogeneity is something that physicians have been trying to do for centuries. So they would argue that personalized medicine is nothing new. So what is the new piece about this? Well, the perspective I want to present is that the idea today is that this is a targeted area of research, and the idea is that these are empirically based, reproducible, generalizable results about how to precisely or more precisely prescribe medicine. And so there is a data-driven aspect to it, and there is a statistically solid aspect about it, which is very different than the traditional approach to personalized medicine. So I want to give a few more details about this. There are many aspects of an individual's data that could be brought to bear to construct a treatment or to develop personalized medicine, precision medicine: genetic makeup, proteomics, metabolomics, metabiomics, environmental factors, demographics, lifestyle, diet, many other possibilities. And there are many scientific tools that are brought to bear: biomedical knowledge, just generally speaking, many kinds of data, as I mentioned earlier. And there are two primary approaches to precision medicine, or ways of thinking about it. These aren't exclusive exactly, but they're useful to think about. That is knowledge-driven versus data-driven. And I want to talk a little bit more about that in just a minute. And of course, there are mathematical, statistical, and computational tools, many of which we have yet to develop, but we have a few that are available. But one of the points I want to make is that there are many open questions. So this is a ripe area for statistical research. So knowledge-driven, well, this is the idea that if we know everything about an individual, we can mathematically model everything about them at the cellular level, at the organ level, the system level, at the individual level, at the environment level, If we do that accurately enough, we can give exactly the right treatment everybody has. And there are people that actually believe that that is the realistic goal that we should set. But if we think about this, those who've been involved in this kind of modeling, really it's conservative to think that we would probably take a couple millennia before we get to that point. So what is the realistic things that we can do to move forward a little bit faster? So data-driven approaches are very helpful here. And the idea here, of course, is using larger, small data sets that are well designed, computational methods, statistical analysis tools that let the data guide us towards how to construct a precision medicine for people. The challenge for this are that the methods for this are still being developed, and there's a lot of ideas that are floating around there that are not rigorously worked out or evaluated. And so, as I said before, this is an area that's very open right now, and we really have a large gap in what we can do effectively here. But I want to mention that the real wise way to do this is to have a hybrid approach where we let scientific knowledge and other things guide us in how we set up our data-driven approaches, and that we use those to inform the knowledge. We go back and forth. This is the realistic and the better approach. I do want to clarify that, because there are some people who advocate knowledge-only approaches and some people who advocate data-only approaches. A little more about the knowledge-driven approaches. It is valuable and important to understand enough biology to figure out how we can treat illnesses. And there is research being done to accomplish this, and there's research at multiple scales that I hinted at earlier. And then in the modeling that's being done, it usually has to integrate across multiple scales. If you model accurately one system, such as the immune system, you still have to model how the patient will respond to the right sorts of care in the hospital, or to other aspects that are part of the health care that are outside of this particular system we look at. So the challenges are there's multiple systems. I just raised that point. I'm not exactly sure what my end point here is, except to just say this is really hard to do. Okay. The data-driven approaches can really help us, and the advantage is that we don't have to have complete knowledge, but we have to have some to know where to start. And we can actually do the data-driven approaches at multiple scales simultaneously with a little bit, without quite as much work as the knowledge-based approach. High throughput methodologies are very useful. A common approach that many pharmaceutical companies will take to precision medicine is to identify a well-defined genomic subgroup. For that subgroup, they find one that has the biology is very clearly understood. And so they can go in and then give a specific treatment that will affect that subgroup. So an example of this, several years ago, GlaxoSmithKline developed a lupus treatment. And this lupus treatment, this is a chronic disease, this lupus treatment worked on 5% of patients with lupus, but they had the right biology for this particular treatment. So they kind of went back and forth between, okay, what subgroup can we work with? Do we understand the biology? Until they found this nice combination. Now, our approach, our group has been focusing on is quite different than that. We're not trying to find a subgroup that will benefit from a specific type of biology. We want to see how we can take the entire population and treat everybody. How do we decide who should get which treatment? So and one could argue that there may be an economic thing going on here. I'm an academician, so I'm not trying to make millions of dollars doing this, whereas pharmaceutical companies, they have to think a little bit more economically about how much will we get for a payoff. But I think that that looking at the whole population is a very worthwhile approach, and it also is an opportunity for statisticians to have a lot of influence. And we can construct specially designed clinical trials, and in some cases we can work with large complex data sets if we're careful about it to accomplish this. So I want to talk a little more detail about the statistical and computational tasks that I'm focusing on here. What we want to do is we want to develop methodology that is reproducible, generalizable, one approach that we'd like to take is efficient clinical trial designs to accomplish this, to discover these individualized treatment rules. And I'm going to give a very precise definition of what I mean by that, but the simple idea is that you collect some variables that are prescribed for a patient, you look at those variables, look it up in a table, and it tells you what treatment to give them. That's what I mean by a treatment rule. And in the case of a sequential treatment over time, such as what would happen with chemotherapy in treating cancer, we would collect data over time as well and use that to guide our initial treatment and how we would change treatment. Okay? But these are potentially, in many settings, we don't necessarily have, we have a large number of biomarkers, and there's no scientific reason to narrow that down. And so we have high dimensional problem here, at least moderately high dimensional. I want to just clarify here that, repeat my statement earlier, that we're not looking at individuals just as individuals, but we're looking at them as they are summarized by a vector of data points on them. So it's not purely individualized treatment, as I mentioned earlier, but it is stratified or precision medicine where we're being very precise. We're just not working at the individual level. So what are some of the challenges? Well, some of the challenges, we don't really know ahead of time what these right treatments are. We may have a list of several treatments that are candidate treatments, but we don't know how to match it up. That's the whole purpose of this research, is to figure this out. But we could have high dimensional predictors. There could be arbitrary interactions. We could have longitudinal data that has sequential dependency within it. So, and in all of this, we want to keep ourselves attuned to the clinical focus. We really want to make the best treatment decisions based on the data that we can. Okay, and so it's useful to divide this up into two major approaches or types of issues. One is the single decision setting. This is the question of a patient presents with a disease, you have the data you're supposed to collect, and your job as a clinician is to give them the right treatment. That's a single decision situation. Multi-decision, as I mentioned earlier, you have an initial decision, what's the best initial decision, depending on how they respond and other measurements, you'll have a second chance when you look at it again and give them a different treatment possibly, and you continue doing this until the end of the treatment. And you want to accumulate historical data and use that as you go along. And an important point with the second group is that best decisions take into account delayed effects. You can't just break up the different decision times into individual clinical trials and then piece it all together. You can actually prove, there's actually an interesting cancer data, clinical trial data set that illustrates this, where you'll actually get misled, and you'll give something that is suboptimal if you do that. But that's what people have done historically. So we now know that's not the way to do it. You have to take into account these delayed treatment effects. And then biomarkers play an important role. And you could think of biomarkers in a lot of different ways, but the two distinctions I want to make here are the difference between a prognostic and a predictive biomarker. Prognostic biomarkers are very good at predicting how a disease progresses, how long a person will live, and this sort of thing. Predictive biomarker tells you, in addition, how treatment is going to be affected. So predictive biomarkers tell you which treatment they should get. Prognostic tells you what the outcome will be. It turns out it's very easy to show that those two are orthogonal quests, so that you can have something that's a great prognostic biomarker that has zero value as a predictive, and vice versa. Although most people consider predictive biomarkers to be the harder ones to develop, because that requires treatment information in your data set as well as feature variables and other things. And I'll come back to that a little bit later. So I realized that we talked about machine learning a little bit in the panel, not we, but the panel did yesterday. And I think that this is a very important area for us to think about. And I want to mention a little bit about this, because machine learning is a set of tools that is very useful for this question that we have. And since machine learning is a form of data analysis, as statisticians, we own this area just as much as anybody else does, and we should be more acquainted with it. But these are a collection of methods for automated learning from data. Learning could be classification, it could be regression. It turns out that there are actually a bunch of other things it could be that don't fall into the category of either regression or classification. And many of these ideas originated in computer science and related areas. And many of the ideas also originated in statistics. And the best machine learning tools have good statistical properties. That just goes without saying probably, but it has to be true. One of the things, there's a term called zero order inference. This is not variability. This is just simply knowing that a procedure is consistent, that it estimates. Sorry, is that better? Do you miss everything I said before? I'm really sorry about that. I can't hear back. Do I need to start over or? Okay. All right, I'll keep it closer here. So the best machine learning tools have very good statistical properties, and one thing I wanted to mention is that it's helpful to at least establish consistency of these approaches. And some of the approaches developed in computer scientists from computing don't necessarily have that property, or they don't know whether they have that property or not. And so this is an important step. And statistics can do a lot to improve machine learning, but machine learning can help statisticians think in new ways about learning from data. And there's a term that's used by many people called statistical learning, which is really all of machine learning, but just reminding people that actually, when it comes down to it, all of data science is statistical. So really, we have ownership of machine learning, so we'll call it statistical learning. Well, that hasn't caught on with everybody, but I like the idea here. And there's a very classic book here that is actually out in I saw it out in the Springer display that I recommend people look at. But these traditions, to be honest, are coming together in many ways. There's people, computer science and statistics working together, but there's still large gaps between these disciplines. So, I got to hold the right place here. Sorry about that. So one thing I think is important is to just talk a little bit about what is machine learning and kind of answer some questions here. So is it really just statistics by another name? Well, the answer is partly yes and partly no. The yes part is that pretty much lots of things that we do in statistics are machine learning too, like logistic regression, classification, other kinds of regression, linear regression, all of these things. And we use those to summarize, predict, or learn from the data. But there is also a no to this. Some of the non-statistical approaches bring unique strengths and a different way of thinking about data-driven thinking or learning from data. Support vector machines, for example, this is an alternative to logistic regression, but what it does is it seeks to only identify the sign of the probability, conditional probability, minus a half. So it doesn't have to get all of the terms in that probability right. It just has to get the sign right. Now you say, well, why would you want to do that? Well, it turns out that if you do that, you can handle much higher dimensional data with many more interactions and do a very good job. Now, what's the drawbacks of doing that? Well, really inference is very difficult because you're not getting the whole function. And so one of my colleagues says that what really is often one of the cultural differences between machine learning and statistics is that oftentimes machine learning is developed for one specific task. But with statistics, we tend to do things for multiple reasons. We build a regression model to predict, but we also want to understand how the covariates are affected, how the covariates affect the outcome. We want to learn something from the model as well. And that's a good thing, but sometimes the prediction is so important, you may want to sacrifice your ability to understand the model to be able to predict well. And there's other things about machine learning. There's certain estimating decision rules from data that really cannot be considered classification or regression. It's a completely different task. I may point that out if I can a little bit later, but there are lots of situations where we want to use the data to make a decision, and modeling the data does not need to be a part of that. We can just get the decision directly from that data. I'll try to point that out when we get to there. So one of the areas that sort of illustrates a little bit of this is something that we've been working on called outcome-weighted learning, which is a way to use machine learning, some of the benefits of machine learning to help in this precision medicine quest. So I'm going to start giving some formulas now. So I mentioned earlier that we have a vector X that we collect on each patient that tells us about that patient. We want to use that information to help us make a treatment decision. So if we design a clinical trial for that purpose, we would potentially randomize patients to treatment, and we would collect the X data as we go in the clinical trial, and then we'd also assess an outcome R. And so R is the clinical outcome. It's just a positive number. The bigger, the better. And there's something called the Q function, which is a key part to doing this, and it's just simply the expectation of R given the X variable for the patient and the treatment. So you can see that's just a regression, right? That's all that is a regression. And so one very simple way to get a decision rule from this is to estimate that regression, maybe non-parametrically or parametrically, whichever you prefer. And then what you do is you construct the decision rule D hat for each value of X, you plug the X into the Q hat, and you pick the choice of A, which is better. So A is the two treatments, say, and so you pick whichever treatment is better, and that will be the treatment you give to that patient. So you can construct a table from this, or you could look it up, program it very easily, and get a treatment rule for that patient just from this regression. Now, so what you're going to have in that regression is the interaction between the treatment and the feature variable. So if we were to just put down a simple model where we had some function of X, where R was predicted by a function of X plus the interaction between A and X, that would be a very simple model. And it turns out that the first part of that function would be a good prognostic biomarker, and the second part, the interaction part, would be a good predictive biomarker. But the disadvantage is that you have to model this model. It's very rich, and you must do the interaction terms, because that's where all of the information about what treatment to give them lies. And so if you want to do this non-parametrically, this is a very, very big problem. And not only that, but the inversion of this that you get is actually going to be less stable than the original regression. So you have some potential multiple opportunities for increased noise and increased bias. So let's talk a little bit now about the idea of a value function. And this is leading towards this idea, the simple idea of outcome-weighted learning. So we're going to have a probability distribution for X, A, and R. We've done randomized study. We're just going to use that. And they're randomized according to the rule pi A given X. This is just a distribution of the treatment given X. So in a normal randomized trial, this would just be 1/2 for the treatment 1 and 1/2 for treatment -1. We use 1 and -1 as our coding for treatment. And so there wouldn't be any function of X, but you could randomize according to X. It turns out that there are situations, something called Thompson sampling, that if you do randomization that way, you get increased accuracy in estimating the rules. But we can just take a simple randomized trial and think of this as constant probability for each treatment. But we just have that generally. Oh, another thing I want to mention is if you don't have a randomized trial and you have an observational study, the pi of A given X is your propensity score, which you could estimate. So you could apply this to observational data, but you'll need to have some basic good properties of your observational data. The data can't be too biased. You need to have your pi bounded away from 0 and 1, for example, over every X. Now the value function is simply, for a given treatment rule D, that's simply the expected outcome for the patients in my population, given conditional on me using rule D to assign treatment. Okay? So it's just a conditional probability. And it turns out that I can just write down the little integration here, and I get something that's as you go across this, you get in the end, the value function can be expressed as the expectation under the original distribution, or under the distribution generating your data, of the outcome times something. And that something is the indicator that the treatment they actually got coincides to the treatment rule, divided by the propensity score. Now that has expectation 1 if you look at it by itself, just by construction. But this little random weight is a radon nicotine derivative, and you can look at this another way. And the other way is you can look at this as classification accuracy, I of A equals D, multiplied by a weight, R, divided by pi of A given X. Now it turns out that the optimal rule is given below, and it's simply the Bayes rule. Okay, and you could do it if you could apply it. You could obtain this rule if you have these estimates of these expectations, which comes from your Q function. So from your Q function, you could directly get the optimal rule, but you have to know it exactly. So what we're working toward is a way to get at that rule with only have to estimate the sign and not the full function. Okay, so how do we do that? So maximizing that value function. So the idea is I want the treatment rule that will maximize my outcome for this population. In other words, it will perform the best on average of any treatment rule. Now, it could be that if everybody should get one treatment, your treatment rule is that everybody gets that treatment, and that's an okay treatment rule. So in a randomized trial, it might end up being the case that your drugs you're comparing, one of them is better than the other for everybody. But that's probably not going to always be the case. So this will allow you to have a situation where sometimes a drug is better for some people, sometimes it's better for another person. So maximizing that value function is the same thing as minimizing the risk of putting the A not equal to D there. And this is, you can take that quantity up there and you can write down in empirical form, and you get this quantity right here. I think this is going to give me, hope I don't break anything. I don't want to push any buttons and have something happen. So the blue expression at the bottom there is a very simple empirical expression, but what you see is there's this indicator that A doesn't equal to D of X, and we're going to let D of X be just simply the sign of some F of X, okay? But what you see is that is a weighted classification error, okay? So if I view it this way and I minimize this, then technically I should, going back, if everything asymptotic, if this estimates the right quantity, I should get the treatment rule that actually, truly in the true population, maximizes expected outcome. But what's really odd about this is that this, on its own, this classification doesn't make any sense. If you have a randomized trial and you're classifying the treatment people receive, it should be completely random, right? There should be no association, so you should learn nothing. But what this tells us is if I recast it as a weighted classification problem, it's exactly what I need to get me to figure out what treatment people should be getting. And so this is a starting point here. However, this particular optimization, quantity optimized, is not convex. It's not continuous. And so here's where we bring in machine learning. We replace the indicator of being the correct classification with something called the hinge loss surrogate. This is a continuous function that is an approximation for the stump or the misclassification error. And then we add a penalty to control the smoothness of this. Now this is exactly what the support vector machine is. The only difference is that there's no r over pi ax in the beginning, just the empirical sum without that weight. And so it turns out that this can be recast as exactly a weighted support vector machine, which means I can use the full power and strength of support vector machines and all of the advantages that it brings with this flexibility to do this. And I talk about how to do this with a linear rule. We would then penalize F with the Euclidean norm, some penalty lambda, and we'd estimate the treatment rule this way. That expression is very easy to, compared to the one on the previous page. It is convex and continuous, and you can come up with a universal solution, a guaranteed universal optimum. This is an OWL, OWL, outcome weighted learning, so I like to just put that up there. Okay, some results, and I'm not going to go into all the details of this, but some results from this O-learning technique. It turns out that we can use something called the kernel trick in support vector machines, which allows us to use any kernel we want, including a Gaussian kernel. The long and short of this is that we can have non-parametric functional forms very easily with very little difficulty. We have one more nuisance parameter we have to estimate or tune in addition to the lambda, but that's all we really have. It turns out that it's Fisher consistent. This means that even though I used a surrogate for my optimization, not the true classification classification error I was trying to address, it still gives me the right answer. The parameter it estimates is the correct parameter anyway. So it gives me Bayes' rule specifically. It's asymptotically consistent, which is more useful for statistics, and model robust. So it turns out that I don't have to have my model right for this to work. I can skip the accuracy of my model. The only thing I have to have is if my class of functions I'm using, it has to be relatively rich so I can capture the boundary between people who need treatment A, treatment 1 versus treatment -1. But if I misclassify or misspecify that, I'll still get the best line that separates or best shape that separates this. So this will give me something that will work even if my model is completely wrong. So that's a very nice feature about it. Now I want to mention a little bit, this is another thing that's different in machine learning thinking and statistics, in that we often use a likelihood in our inference, which is a very good way to go, and we directly know how the parameters of what we're estimating relate to the likelihood or the distribution. Well, because I use a surrogate, this doesn't correspond to maximizing a likelihood. And so what's important is to show that the parameter has meaning in the distribution. So that's why Fisher consistency is actually an important idea, because you're replacing what you're estimating with an alternative approach, but you want to show that the parameter is still what the target parameter is still what you want it to be. Okay. Turns out that they have very accurate risk bounds. The rate of convergence of these support vector machines can be very rapid. If you have a linear boundary, finite dimension, it can be basically n rate of convergence, which is faster than the usual square root of n. But generally speaking, it'll just be some other rate less than that. This procedure achieves the same level of optimality in terms of rates as support vector machine does. We utilize this on a very interesting depression clinical trial, and it showed that it did identify a treatment rule that was better than any of the fixed treatments, and it seems to work very well overall. It's an example of this direct value approach where you focus on the value function. There is an alternative approach where you can do a similar thing, but you can set it up as a semi-parametric regression model or double robust semi-parametric regression model. The differences are you still would have a likelihood, and we're still working on. We've been able to figure out that there are many situations where you can use a likelihood to actually guide you or inspire a new approach to support vector machines, but there are also many support vector machines that do not correspond to any likelihoods. So there's an interesting relationship between those two. One thing it does is it opens the door to using machine learning in this very difficult statistical problem. Okay, so I want to talk a little bit about some extensions of this idea. First off, our approach did not initially allow for censoring, so we extended it to allow for censoring in Biometrica paper. It's not a perfect approach, but it works pretty well. We still have to estimate various terms in the survival, the probability. We have to estimate the probability of censoring in some cases. We've also extended it to multiple decision times. So this is the case where we had the more complicated situation where you had to take into account delayed effects. We were able to extend it to that. And what's interesting there is, again, you don't have to model. There is some challenge, though. And so here's full disclosure. There is a weakness to this approach. And I'm going to just mention this briefly. Let's go back to here. So, no, here. Okay, so right here. No, I think it'll look better here. So if you see this sum on the bottom here, if A happens to equal the sign of f of x, that expression is 0, and so it's not going to contribute to the optimization routine. And so in other words, approximately half of the data is not used at any one time when you're trying to estimate this. And that's approximately true with the surrogate approach. And what happens when you have multiple decision times, you actually get 1/2 or 1/4 if there's 2 decision times, 1/8 if there's 3. And so the price you're paying for not requiring the model to be correct is you have to use less and less of the data. So one of the approaches we've been developing is where we have a doubly robust approach, where if the model is right, you get to use all the data. If the model is wrong, you only use this fractional part. And you can show that this approach will give you the best of both worlds, depending on whether the model is right or wrong. So there are ways to think about this. But still, the advantages are your model does not have to be correct for this to work. Okay, some other minor errors, issues have to do with lack of invariance under constant shifts in the outcome, which led to further improvements. And how to handle observational data. I mentioned you have to estimate the propensity score. And how to handle multiple treatments. So in machine learning, when you're classifying more than 2 groups, 3 or more groups, that's a difficult problem. There's a whole bunch of different approaches to doing it. Of course, since I'm trying to bridge this question into the machine learning area, the same problems that happen in machine learning are going to carry over here. But there are some very interesting ways of thinking about this for multiple categories, especially if they're ordinal. One of the things that we've started recently working on is the extension from 2 or 3 treatments to a continuum of treatments. So this would apply as if you want, this applies to the problem of identifying an individualized dose for each patient. And so this is something that I'm going to talk a little bit about right now. This just is a little bit of an advertisement. If any of you are going to joint Cisco meetings, what I'm talking about now will be a discussion paper in the JASA Theory and Methods discussion forum, but I want to give you a little idea of what we tried to do. So this actually was motivated by a collaborative a consultation experience I had as a biostatistician. Some clinical researchers came to us and said, we're treating patients with bronchopulmonary dysplasia, BPD, and these are preterm they're preterm babies, and they're low birth weight. And this is a very serious risk factor. In the U.S., if a baby has bronchopulmonary dysplasia, about 20% of those patients go on to have pulmonary arterial hypertension, which is very serious and about 40% death rate. And so trying to prevent that second arrow there, or the second arrow is very important. And so what they do is they have a drug that seems to be effective and to really improve the outcome for these patients, but they have no idea what dose to give. So they came to us saying, can you help us figure out a way to find the right dose to give these patients? Meaning, not just, they weren't looking for a single dose. They wanted every different patient with different weights and different features to be given the dose that was right for them, because they could tell that there was not going to be a simple rule for the dose finding here. And so sildenafil is the dose, is a drug that works here. And so that was a motivation for this. Now, we thought this would be an opportunity for us to ask the question about whether we would be able to extend this outcome-weighted learning to this problem, since not having to worry too much about the model could be very helpful in this situation. So so I want to just compare this dose-finding problem with a more traditional pharmaceutical dose-finding task. So let's pretend we have 40 patients, and we're going to try to find the optimal dose for these patients. One could construct a very simple clinical trial where you just assign different doses, and you assign, in this case, let's just say it looks like 8 patients per each of these doses. And the one with the highest recovery rate, 5%, would be the dose that you pick. However, the clinicians would tell you that doesn't make any sense, because I know that a very early term baby will need a lower dose. It's going to be too much for him. And I know that an older baby with more severe BPD would need a higher dose. So we can't use the traditional pharmaceutical design for this. So let's look at exploring now the possibility of using outcome-weighted learning in this case. Well, one challenge is, you remember we have that expression about the treatment has to be equal to the treatment rule. Now in this case, we're not looking at the sign. We actually have to estimate the whole function, because this time the function is going to be what dose they get as a function of x. So it's a very hard task. But when I say I'm trying to minimize my modeling, I don't want to have to model the whole distribution here. I just want to have to model the rule, the dose rule. I don't want to have to worry about all of the probabilistic modeling. All right, so the challenge is that you need patients with the same dose to be able to apply this. And if you have doses on a real continuum, the probability that they'll match your dose is actually 0, right? Because of the Lebesgue measure issue. And so a simple thing to think about is just, let's create then a kernel around the dose and capture those patients that are close. kind of weight them by how close they are. So that's the basic idea, and that leads to this this function here, which I'll show you, give you a picture of so you can see it. On the left, this is how we would weight the patient. It's a very simple idea. Just if they're close, you get the most credit, and if they're far enough away, too far away, we wouldn't want to count them at all. Now, turns out that if you convert this to a loss, which is what we want to do for applying machine learning techniques, it would look more like what's on the right. Now, I just want to comment briefly that this is unusual for support vector machine or machine learning, because usually you try not to bound the loss. You want to have a convex function here. And this is not going to be convex. It's truncated, right? So it won't have it. So this is going to be a problem potentially. We'll talk about how to deal with that later. However, a very interesting result is that if we use unbounded loss function, we can actually prove that it'll be inconsistent. So not only is it inconvenient, but it'll give you a wrong answer. All right, so this is sort of the optimization function we want to optimize with our surrogate in there. And the penalty, we can have a linear dose rule, or you can add higher terms so it'll be more quadratic or whatever you want it to be, or you could have it be nonlinear too. So we maximize this. Because it's not convex, we don't get a lot of the benefits from a lot of the computing tricks we can use for support vector machines. However, there's something called a difference of convex algorithm we can use because you can show that this is a difference between two convex functions. And that gives you some nice computational advantages. So we utilize that. And the result in this case is we can prove that this method is consistent. The convergence rate is able to get close to n to the minus 1/4, which you may think that's really slow. However, keep in mind the difficulty of the task. We're looking at a non-parametric, high-dimensional function with many, many variables. We want to get the right dose. Turns out that if you do, another way you could do it, you could build that full regression model and invert it. This time, it's many, many orders of magnitude more difficult problem, and the convergence rates will get much, much slower if you're doing something non-parametric. So this is actually a pretty good convergence rate. And we can generalize observational data, and the simulation results are very promising, and it works well with a warfarin dosing data set. So that's just a little bit of an introduction to that idea. More details can be found if you attend the JSM session. Now I want to talk a little bit more about another idea that is related to this. And this, how much time do I have? What is my, huh? Oh, okay, phew. All right. So I mentioned earlier biomarkers, and I want to kind of link back to this idea a little bit. And now biomarkers are usually used for prognostic purposes to identify people who have the disease or who don't have the disease. So you might use, the biomarkers I want to focus on at this point are prognostic. I'm thinking about classification of disease or infection status or something like this. And so the section I just finished with looked at predictive biomarker development. Once I have that rule is a predictive biomarker. It's a very precisely used biomarker. It tells you exactly what treatment to give, but it is a biomarker. And so I want to talk a little bit now about about prognostic biomarkers. And in the simplest situation, you have a single continuous biomarker, some sort of blood test or something, and you want to look at some sort of cutoff for which you want to declare the person has the condition or they don't, or you want to call them back in for a second layer of testing. So the question is, how do you decide where to make that cutoff? How do you decide how good your biomarker is? And there's something called an ROC curve, which gives you a feel for all of the possibilities of all of the cut points and helps you determine what is the best trade-off between sensitivity and specificity for that. So one of the things we'd like to do is utilize machine learning to help come up with a fully non-parametric approach to ROC curve estimation that can give a person who's trying to develop a biomarker an idea of whether or not they're making optimal use of their data. So think of this as, one could also use this to create a biomarker, but this could also be used for evaluating simpler biomarkers, whether they work. So So what's the problem with using SVM and this is going to be fairly simple. It's not a trick question here, but it may seem like it. What's wrong with using support vector machine for developing a good classifier for using a biomarker or a collection of biomarkers to decide what treatment to give people? Well, the problem is that it estimates the sign of the probability of the person having that status minus 1/2. Well, that's only 1 point on the ROC curve. But usually you like to look at this whole curve, and very seldom is that the best point to use for the particular situation you're considering for the trade-offs. We discovered this when we were working, discovered it again. We were doing some classification, just taking genomic data and trying to predict who is going to respond to, be responsive to breast cancer treatment that we were studying. And what we found is that the support vector machine had a limit to how good it could do, because sometimes when the particular thing you're looking at has a probability of occurrence that's away from 0.5, you need a different point on the ROC curve, and the difference can be very dramatic. I think that in some cases it can be a 30% improvement in prediction accuracy if you pick something different than the one that the SVM would normally pick. So how do we get around this limitation? So the idea here is very simple. Let me just talk a little bit about the data, present the idea. So the data here is a little simpler than the data I had before. We just have the thing we're trying to classify or predict, the disease status, A, and we have the X variables, which is our collection of biomarkers we want to use. And the goal is to estimate disease class based on all the available data. So I'm going to define a weight function, which has this form here. The point of this weight function is that as alpha is 0, then this is just, so let me back up a bit. If alpha is 1/2, then this weight becomes exactly 1. Okay, so the weight becomes 1 if alpha is 0. I mean, alpha is 1/2. That corresponds, when I'm going to all said and done, that would correspond to standard support vector machine. By shifting alpha, I'm going to this weight's going to move from one function of the indicator of y to another. The point is it just varies from 0 to 1. I'm not going to go into too many details here, but what I want to do is I want to, instead of doing the standard classification, I want to do a weighted classification. So this is similar to outcome weighted learning, but I want to use this alpha parameterized weight as my weight. Okay, and then I want to do weighted support vector machine. Okay, and we can use a Gaussian kernel here. We want to use the usual surrogate that we would use, hinge loss surrogate. But now what we have is, instead of standard support vector machine, I just have another weighted support vector machine, but this weight's different than the one before, depends on alpha. And it turns out that if I do this, just the long and short of it is that this will allow, at every point, if I vary alpha, I'll get every point on the ROC curve. And the nice thing is for each alpha, this will be the optimal decision rule for that particular point on the ROC curve. So you can prove that it's Neyman-Pearson optimal. And so this just shows that I can get every possible value of sensitivity and specificity as I range over alpha. There isn't a simple correspondence between alpha and sensitivity. It's just guaranteed to cover the whole territory. And then what you can do is you can look at your curve and then pick your best alpha based on that curve and make a better choice. Okay, so it turns out that really what's happening is Neyman-Pearson-Lemon Bayes theorem yields that for a given choice of alpha, the optimal classifier is given according to this rule here, which is basically the sign of the function on the left minus 1 minus alpha over alpha. So when alpha is 1/2, that would be 1. And this is just a transformation of the usual probability that you get with support vector machines. So things aren't exactly 1 to 1 here, but alpha equals 1/2 corresponds to the sign of the logistic regression prediction minus 1/2. And all we're doing here is we're changing that 1/2 to various values that allow us to get everything on the ROC curve. And so all we have to do is estimate the sign of that. We again get all the benefits we get from support vector machine by not having to fully estimate that whole function, but just its sign. But now we do this for each of these alpha values, and that's actually quite easy to do. And here's some interesting results. First off, if you look at the function that you get as a function of alpha, it's Fisher consistent, our approach, asymptotically uniformly consistent. So this approach will get you the uniform consistency over all of alpha, and that means you can smooth the curve to get a good visualization of this. Simulations show that this works extremely well. It does seem to get the optimal most of the time. So here's just a little example here. This is a simulated curve. There's a popular approach called the semiparametric ROC curve, which we use as a comparison. And then there's the empirical base, which is just empirically trying each possible cutoff and looking at how that performs. And you can see that what you want is you want this to be as high as possible. And so this approach does give you the highest, and you can then get an idea of how close you are to the optimal. If you don't want to use that fully non-parametric, you want to use a simpler one, you could see how much you have to sacrifice by doing that. And in some cases, you may want to use this fully non-parametric approach. We use this on a simple example of where we're trying to evaluate. We just had two biomarkers, PCR-based and ELISA-based, for predicting hepatitis. And you can, if you get each of the individual optimal choices on the ROC curve, you get sensitivity specificity given in the table here. But if you use this approach, you can significantly boost your sensitivity, and you lose a little bit of specificity. But for this particular category of problems, this is a much better balance. I'm almost done here. Okay, so as I said, so some concluding thoughts about this. I think this is a very exciting time for precision medicine. It's at the confluence of machine learning, big data, biostatistics, data science. I think this idea of outcome-weighted learning, or O-learning, and related methods bridge between machine learning and precision medicine in a very useful way for us as biostatisticians. There are numerous open questions, but I also think that this work is part of an emergence of a new or renewed discipline focused on data-driven decision-making. And I think biostatistics is starting to have a lot of influence in that. These are a bunch of collaborators that I have. Some are statisticians, some are clinicians, and some are students. So, thank you.
Well, questions to Michael?
I would like to ask you, how do you think the importance of clinical trial planning, the clinical planning role in improving the performance of these methods? I would like to be a bit more specific. As soon as I noticed in the beginning of your presentation, linking the knowledge-driven and data-driven approaches, it seems for me that the priori knowledge could be incorporated in the planning, sampling or allocation planning. And I don't know if you agree, and what are comments.
I agree completely that you can use prior knowledge. Now, I glossed over that issue. I mean, there's many issues we could talk about, so I didn't spend as much time on that. But you're absolutely right. In the simple way, you would want to use clinical knowledge to choose those variables, X variables. Now, while you may have 1 million variables to choose from, this procedure cannot function with that high a dimension. It works very comfortably with 50 dimensions, which is still pretty big, but that means there's a lot of knowledge that has to go in to winnowing down your selection of biomarkers. Now, another thing is that you could do more precise things. Right now, for some of these tasks, it's not clear how to do Bayesian approaches. But I believe that there exists some nice Bayesian approaches that could allow you to use prior knowledge that way. And I know, in fact, that there are a couple areas where that's very useful. I will say that one of the disadvantages with Bayesian approaches generally is that usually you have to specify the whole distribution. And a lot of the point I made today was avoiding having to model that correctly. And so there's a distinct separation between Bayesian methods and this method right now, but I think that's just temporary. A lot of my colleagues who work more in Bayesian areas than I do have talked recently about the idea of only modeling part of the data and using Bayesian methods that can manage partial modeling. And I think that that could lead to some way of further bringing in knowledge into this procedure. Another thing is that there are ways that one could use knowledge that you gain as you're doing the study to improve your allocation, your randomization, not for the purpose of improving the odds of getting the right treatment to the patient, but to improve your power in getting the right boundary between treatments. Now that's not, and that could be set up probably in a Bayesian way. I'm not clear how to do that right now, but I think it's possible. But I do agree with you that there has to be either more or less formally, there has to be a way of bringing knowledge in, or you really are going to be lost. Unless we had fully automated procedures, which I think are potentially dangerous, where you have it automatically winnow down the number of variables and do everything automatically. I don't believe that that's ultimately in our best interest, though. I think we have to have the scientist in the loop as we go through this. So, but that's a good point.
More questions?
This is more of a technical question. So in your approach for building the ROC curve, as I understand, for each alpha, you have to fit a different SVM, something like that. And if you're doing logistic regression, you could just fit one logistic and then you would have the whole curve. Is there a way of doing all SVMs simultaneously or something?
That's a good question. So we've thought about that. Can you hear me? We've thought about that, but here's the issue again, is that I want to emphasize that the model doesn't have to be right. So the thing about this is that for each alpha, it'll give you the optimal classifier, even if your model, for the class of boundaries that you're allowed, class of curves you're allowing, even if you don't have your probability right. Whereas for the logistic, you have to get it absolutely right. So if you go with the assumption that the logistic model is right, then what you can actually end up doing, sort of as a compromise, is you can pick a bunch of these points of alpha and combine the information across them to get a more powerful. You can think of it as that, sort of as halfway between fully having to specify the distribution that you would in a logistic regression to only have to specify its sign at certain points. Do you see what I'm saying? So there's a natural disconnect between these two. And so this tends to perform much better than logistic regression because you can be off on each one of these alphas. It turns out that you still get that the underlying parameters is continuous even if the model's wrong. So does that help?
We have time for the last question. Come on. No question. So let's thank Mike again.